Welcome to lecture number 8 on matrix methods of structural analysis. Last class we have discussed about the analysis of a symmetrical portal frame. Geometrically as well as load wise we have analyzed a symmetrical portal frame. In this lecture we will take up an unsymmetrical portal frame. This is the portal frame. Analyze the portal frame loaded as shown in the figure by matrix flexibility method. Now this is of the bay width 6 meters, left hand side column 12 meters height, right hand side column 9 meters height. It is subjected to UDL over the entire span, and also at the center mid height of this column there is a lateral load of 48 kilonewton plus there is a horizontal force of 16 kilonewton at the support B. This is the frame. Left side it is fixed, right side it is hinged. So in all aspects it is unsymmetrical. So we will discuss how to analyze this unsymmetrical portal frame. So as we know that the first step in the analysis is finding out the degree of static indeterminacy. So the degree of static indeterminacy is equal to number of closed loops into 3 minus number of releases. That is equal to, this is one loop, number of closed loop is 1 into 3 minus number of releases. Left hand side it is fixed, therefore there is no release here. It is not free to move in the vertical direction, not free to move in the horizontal direction, and also not free to rotate because it is fixed. The effect of fixing is to make the end slope equal to 0, therefore no rotation also. Here coming to this can take a vertical reaction component, this can take a horizontal reaction component, but it is free to rotate. So there is one degree of freedom, it is free to rotate. So that is otherwise called release. So number of release is 1 at D. At D it is free to rotate. Therefore 1 into 3 minus 1 equal to 2. So this structure is statically indeterminate to 2 degrees. So this is the given structure. So what we have to do is we have to first find out the degree of static indeterminacy, then convert it as a statically determinate structure, or we have to convert it as a primary structure. So the given structure we can do it in a number of ways. What we are going to do is, let us release the support D. Let us release the support D. At support D we have to mark the redundance. So this is one redundant, that is the vertical reaction at D and the horizontal reaction at D. These are removed. So let us call this as F3 or F0. We will give the number later, F0. This is also F0. These are the redundants. So we are treating the vertical reaction and the horizontal reaction at D, we are removing them and make the structure statically determinate structure. Therefore this structure is a primary structure, primary or statically determinate structure. Right. After that we have to find out the fixed end moments. We have to find out the fixed end moments. So in span AB it is subjected to central load. So M of AB equal to minus WL by 8 equal to minus 48 into span is 12 meters, WL by 8. So this will become 6 into 12 minus 72 kilonewton meter. M of BA equal to plus W L by 8 equal to 48 into 12 by 8 equal to plus 72 kilonewton meter. Then M of BC equal to minus W L square by 12, BC subjected to UDL over the entire span, equal to minus 24 into span is 6 meters, 24 into 6 square by 12 equal to, so this 6 square will be 36, therefore it is 3. So minus 24 into 3 equal to minus 72 kilonewton meter. M of CB equal to, it is plus WL square by 12. So substituting, you will get plus 72 meter. M of CD equal to M of DC equal to 0 because CD is not laterally loaded. So that's about the fixed end moments. Now, these are the fixed end moments. So here it is minus 72, here it is plus 72, here it is minus 72, here it is plus 72, here it is 0, here it is 0. In addition, it is subjected to a lateral force of 16 kilonewton. So equivalent joint forces which will be necessary at the end will be plus 72 minus 72, then plus 72 minus, that will be the equivalent joint forces that will be required at the end of the problem. Right. Now, coming to the forces, A is a fixed end. A is a fixed end. There are forces resulting from the given external forces. Since A is fixed, you need not bother about it, therefore forget about it. Coming to support B, in BA it is plus 72, in BC it is minus 72. Therefore, this also will not give any star force. So, plus 72 and minus 72, no problem. Now here, this is plus 72, therefore here you have to apply minus 72, minus 72. So this is one force, F star, force resulting from the external force. There is one more force, this is also F star, but before this, when it is subjected to lateral load, the effect of this is to be added in this, that is why we have to analyze. Now this column is subjected to a lateral force of 48, it is centrally loaded, therefore here the reaction will be 24, here also the reaction will be 24, therefore with this lateral force of 16, you would add this 24 also, so here 16 plus 24 equal to 40 is the value of F star. So here it is 16 plus 24 equal to 40. This is equal to F2 star. This is F1 star. So this is very important. So F1 star is anti-clockwise, which is equal to 72. F2 star equal to 40. This is a lateral force. This is F2 star. So now we have got, and this is 0 and 0, no problem. We have got only two star forces, F1 star and F2 star. So here is a very important point. This is plus 72. This is minus 72. This will not cause any F star value. And here coming to this, now we can give a number. This is F3 now, This is F4 naught. This is F4 naught. F3 naught is the vertical reaction. This is F4 naught. So these numbers we will fix after finding out F1 star and the F2 star, that is F3 naught and the F4 naught. So that's about the. Then we have to fix the element coordinates. Element coordinates will be. So we'll just divide the beam into three elements. So these are the system forces. Actually, these are the system forces. This is primary structure and redundance. Primary structure and redundance. Now, coming to element coordinates, so we'll choose this only. Now, 1, 2, all in the clockwise direction. 3, this is 4, this is 5, and 6. These are element so we have found out the static indeterminacy, we have fixed the redundant structure, we have found out F1 star and F2 star resulting from the given external forces, we have fixed the element coordinates. So with these items we will next take up the calculation of the two important matrices. One is the B matrix, maybe the transformation matrix, and the other one is the assembled element flexibility matrix. Now, first we will take up the transformation matrix B. Now here we have four forces, two forces F1 star and F2 star resulting from the given external forces. F3 naught and F4 naught, they are the redundant forces. F3 naught and F4 naught, they are the redundant forces. Therefore you have to apply F1 star, F2 star equal to unity, F3 naught equal to unity, F4 naught equal to unity. So we have to get the forces along the element coordinates and mark it. So we have done a few problems, therefore now that will not be a difficult job. B will be by applying F1 star equal to unity. So here when we apply F1 star equal to unity, this is F1 star, F1 star equal to unity. So this is a free end now, we have released this. So this is fixed, therefore this is when this is minus 1, this will be plus 1. Now that is for the member equilibrium. For the joint equilibrium, this is plus 1 here, this will be minus 1, and again this will be plus 1. So in this order, it is plus 1, minus 1, plus 1, minus 1, 0, 0. So here it is 0, here it is 0. That is the first column of the B matrix by applying F1 star equal to unity. Now coming to the next one. Now this is fixed here. So we have to apply a horizontal force F2 star equal to unity. F2 star equal to unity. So here we have to apply F2 star equal to unity. So this is 12 meters. 12 meters. So for member equilibrium, when this is 1 towards right, here it will be 1 towards left. These two will cause a clockwise moment of 12, 1 into 12. Therefore, for equilibrium, this will be an anti-clockwise moment of 12 kilonewton. So here it is 0, 0, 0, and 0. Therefore, the second column of the flexibility matrix. So here it is minus 12, 0, 0, 0, 0. 0, 0 along the element coordinates. Right. Now, coming to the next one, F1 star, F2 star we exhausted. Now we have to take up F3 naught. For F3 naught, So let us apply F3 naught equal to unity. F3 naught equal to unity. Now, for this member equilibrium, this is applied, right? So it will be 1 downwards. So this member will be under equilibrium. It is an axially loaded member. Now, for this joint equilibrium, when this is 1 downwards, this will be 1 upwards. Again, for this member equilibrium, when this is 1 upwards, this will be 1 downwards. 1 downwards. So this distance is 6 meters. So these two forces, equal and opposite force, will cause an anti-clockwise moment of 6 kN/meter. Therefore, for equilibrium, this will be 6 kN/meter. That is for that member. Now coming to this joint, when this is 1 downwards, this will be 1 upwards. This is clockwise 6, therefore this is anti-clockwise 6 meter. Now coming to this member equilibrium, when this is 1 upwards, this is 1 downwards. This is anti-clockwise 6. It is not subject to any lateral force, no problem. So this is minus 6, therefore this will be plus 6 kN/meter. Therefore, in this order, these are all clockwise. So here it is 6 minus 6 plus 6. Here there is no moment. We have chosen only moment coordinates, so no moment here. Therefore, that is 0, 0, 0, 0. So that is about the third column obtained by applying F3 naught equal to unity. F naught equal to unity. Now coming to the fourth value, this is the frame. These are the different elements. Now we are going to apply F4 naught equal to unity. F4 naught equal to unity. Right. Now for this member equilibrium, when this is 1 towards left, this is 1 towards right, to satisfy sigma h equal to 0, but this is 9 meters. These two will cause a clockwise moment of 9. We know it has to satisfy all the equilibrium equations. Sigma v equals 0, sigma h equals 0, and sigma n equal to 0. So sigma h equals 0 is satisfied, but sigma m is not satisfied because 1 into 9 will cause a clockwise moment. Therefore, for this it is 9 kN/meter. 9 kN/meter. It requires an anti-clockwise moment of 9. And as we have discussed earlier, for the joint equilibrium, when this is 1 towards right, 1 towards left, 1 towards left, anti-clockwise 9. Therefore, this is clockwise 9 meter. Again, for member equilibrium, as we have discussed earlier, we will not repeat every time. So 1. So this is 1. This is minus 9 meter. Now again, for this joint, 1 towards right, this is 1 towards left. This is anti-clockwise 9. Therefore, this is clockwise 9. Coming to this member, when this is 1 towards left, this is 1 towards right. Now, this is a clockwise moment. When we take moment about this point, this plus 9, because this is 12 meters. 12 meters. So, 9 clockwise, 1 into 12, 12 anti-clockwise. Therefore, you require about 3 kN/meter. 3 meter. So 9 clockwise, 1 into 12 anti-clockwise. Suppose if there is any confusion, let us call this as M. When you take moment about this, 9 minus 1 into 12 plus M. We just call this as M. Plus M equal to 0. Therefore, M equal to, when this goes to the right hand side, it will become plus, this will become minus it is 3. m equal to 12 minus 9 equal to 3. Suppose the direction assumed is not correct, it will be getting the value with the negative sign. So even if there is any confusion, you can just do the calculation like this, you can get the value. That is about the moment. Therefore, the fourth column will be, this is 1. 1 is 3 plus 3 plus 9 minus 9 then plus 9 then minus 9 then 0. This is the B matrix. This is about the B matrix. Now, the first two columns are obtained by using F1 star equal to unity and F2 star equal to unity. So, this is B star matrix. This is by applying F3 not equal to unity and F4 not equal to unity. This is B naught matrix. So, B star matrix is of size 6 by 2, 6 rows, 2 columns. B naught matrix is also of size 6 rows, 2 columns. So, this is one very important matrix. Now, next one is that of the element flexibility matrix. Element flexibility matrix. Element flexibility matrix alpha. Right. For element 1, for element 1, alpha 1 is equal to L1 by 6E I1 I1 into, this is a standard matrix, 2, already we have derived this, 2 minus 1 minus 1 2, this is equal to L1 is 12 meters, L1 is 12 meters, this number, L1 12 meters by 6E, I equal to 2 times I equal to 2 times I, 2 minus 1 minus 1, 2. So this 12, 6 and 2 will get cancelled, this is equal to 1 by EI into 2 minus 1 minus 1 2. This is alpha 1 for element number 1. Now for element number 2, it is L2 6E2 I2, the same formula. Now L2 is 6 meters. L2 is this 6 meters. L2 is 6 meters by 6E into I2 is I. I2 is I. Therefore, 6 and 6 will get cancelled. Therefore, that is also equal to, so alpha 1, this is alpha 1. So that is also equal to alpha 2. Alpha 2. Right. Now coming to element 3. Element 3, it is alpha 3. Therefore, 6, this is L3, 6E3, I3, same formula. Now L3 is 9 meters. L3 is 9 meters by 6E into I equal to 1.5 I. 1.5 I. 1.5 I. Therefore, this 6 into 1.5 is 9. Therefore, 6 into 1.5 is 9. They will get cancelled. Therefore, alpha 3 is also equal to L by 6, 1 by EI into 2 minus 1. Therefore, alpha 1 equal to alpha 2 equal to alpha 3 is equal to 1 by EI into 2 minus 1 minus 1, 2. Right. Now, with these values, we have to get the assembled element flexibility matrix. Now, we will get the assembled element flexibility matrix alpha equal to alpha 1, alpha 2 along the leading diagonal, alpha 3. All other values will be zeros. So this is equal to 1 by EA. In all the three cases, 1 by EA is common. 1 by EA into, for element number 1, 2 minus 1 minus 1 2. So all the other four values are zeros. 0 0. That is for element number 1. Element number 2, 0 0 0 0. 2 minus 1 0 0 minus 1 2 0 0. For element number 3, 0 0 0 0 0 0 0 0. 2 minus 1 minus 1 2. This is the assembled element flexibility, because for alpha 1, alpha 2, alpha 3 all are same. Therefore, by taking 1 by A outside, that happens to be the assembled element flexibility matrix. Now this is alpha, namely the assembled element flexibility matrix. So this is of size 6 by 6. Right. These are the two important matrices. So this is also systematic. If you know LEA, you can easily derive by taking some common terms outside. You can easily derive that matrix. The derivation of this is very, very important. Right. Now coming to the next step. Next step is the redundant forces. Redundant forces. Redundant forces F naught, namely F3 naught and F4 naught, is given by minus A naught naught inverse into A naught star into F star. This is the now F1, the F star is F1 star and F1 star equal to 72, F2 star equal to 40. So this F star is 72 and 40. F star is, this is F star, right? Right. Now, first we have to find out A naught naught. A naught naught equal to as we have discussed this number of times, B transpose alpha into B. This is B naught. So this is equal to B naught is the third and fourth column. So 6 minus 6, 6 minus 6, 6 0 0 0 6 0 0 0 3 9 3 9 minus 9 9 minus 9 0 0 into alpha. Alpha is there. Alpha is 2 minus 1 minus 1 2 0 0. Minus 1 2 minus 1. So this is alpha into A naught not equal to B naught transpose into alpha into B naught. B naught is this 6 minus 6 0 0 0 3 9 minus 9 9 minus 9 0. So this is A naught naught. So 2 rows 6 columns. Here 6 rows 6 columns. So this will give a 2 by 6 matrix. This 2 by 6, this is multiplied by 6 by 2. This is 6 rows, consists of 6 rows and 2 columns. Therefore this will give you a 2 by 2 matrix. So the product A naught naught. So now you are familiar with the matrix multiplication. So straight away I will give you the value. So A naught naught equal to, on multiplication, A naught naught equal to 1 by EI 288 270 minus 270 774. So after multiplying everything, you will be getting the 2 by 2 matrix. 2 by 2 matrix will be this thing. This is A naught naught after multiplying everything. Right. Next step is finding out A naught star. A naught star equal to the same formula. Instead of B naught, here this will be B star. This will be B star. So B naught is same, alpha is same, B star is different. Therefore, this column will be different. The third one is B star. It will be 1 minus 1 1 minus 1 0 0 1 minus 1 1 minus 1 0 0 minus 12 0 0 0 0. So this is there. So again when you multiply the 3 terms, so this product is already available. First one, B naught transpose and alpha is already available. You can make use of the product. With that you multiply B star. So here also this is 6 by 2. This is 6 by 2. So on the same lines, the size of the matrix is not changed. So here also you will be getting A naught star also will be of size 2 by 2. 2 by 2. Now, so A naught star after multiplying you will be getting 1 by EI 54 minus 216 minus 216 minus 72 and 36. This is the product A naught star. A naught star. Right. So we have got 2 important values. Now we need A naught naught star, A naught naught inverse. A naught naught inverse is equal to, so 1 by EI will become EI into 1 by determinant into the adjoint. So 1 by determinant will be 1 by determinant is 288 into 774, 288 into 774 minus 270 minus of 270 and minus of 270 is equal to 270 into 270. Minus minus will become plus, right? So that is this is the determinant into the adjoint of the matrix. Adjoint of the matrix is 774 will go here and 288 will. So this is 774. This will be 288. Now this will become plus 270 plus 270. That is the inverse of the 2 by 2 matrix. Inverse of the 2 by 2 matrix. Therefore, this will be A naught naught inverse is equal to EI by 15 naught naught 12 into this value or into this value, or we can equal to 774 270 288. This is A naught naught inverse. A naught naught inverse. Right. Now redundant force F naught equal to minus of A naught naught inverse. Minus of A naught naught inverse is equal to minus of EI by 150012 into 774 270 288 A naught naught inverse minus A naught naught inverse into A naught star is 1 by EI 54 minus 216 minus 72 36 into F star. F star one value is 72, the other value is 40. As you discussed a little earlier, it is 1. So this will be the redundant forces. Redundant forces will be given by this thing. Now, so EI will get cancelled. So this is 2 by 2. This is also 2 by 2. The product will be 2 by 2. This is 2 by 1. So multiplying these two, you will be getting here 2 by 1. So after multiplying everything, we will be getting F naught equal to 31.26 and 15.74. So this will be the value of F3 naught, and namely the vertical reaction, and the horizontal reaction F4 naught equal to 15.74. That will be the redundant forces. Right. After this, we have to find out the element forces. We have 6 element coordinates. So the forces along the element coordinates, namely element forces P1 to P6, will be given by B into F. Now, B matrix is here. So this is equal to, this is B into F. F equal to B into F. F will be consisting of, we know F will be consisting of F star and F naught now. So F star is 72 and 40. F naught equal to 31.26 and 15.74. These are redundant forces. These are the system forces. These are the redundant forces which I have got just now. These are the value B into F. So B into F will give you the forces along the element coordinates. So here when you multiply first row 4 values by this column, we will get first value. Second row multiplied by this will give you the second value. Like that for 6 rows you will be getting the values 173 minus 173.22 minus 117.9, 117.9, 69.66 minus 141.66, and here last row all values are 0, so multiply with this will give you 0. These are the forces along the element coordinates. P1, P2, P2 is minus 117.9, P3, P4, P5, P6. So these are the values along the element coordinates. After getting this, we have to get the final forces. Final forces F. Final forces P of, you can say. Final forces P final along the element coordinates only. P of equal to P, these values, minus the equivalent joint forces, or this can be P plus the fixed end moments. So that is equal to minus 173.22, minus 117.9, 69.66, minus 141.66 and 0. So that's about the P values. This minus the equivalent joint forces. Already we have got the fixed end moments. So here it is minus 72. So the equivalent joint force will be plus 72. Here the fixed end moment is plus. So the equivalent moment will be minus 72. For the beam, again this is anti-clockwise 72. So equivalent joint force will be plus 72. And here the fixed end moment will be clockwise. Therefore the equivalent joint force will be minus 72, 0, 0. Therefore these are the equivalent joint forces 72, minus 72, minus 72, 0, 0. These are the equivalent joint forces. Now, this will be the final force. So, minus 173.22 minus 72. So, that will be 245 minus 245.22 minus 245.22, because this is minus, this is also minus. So minus 245.22 minus 117.9 minus of minus plus 72. So this number will be minus 45.9, minus 45.9 plus 45.9, 141.66 minus 141.66 and 0. These are the final forces. So for this final force we have to draw the support moment diagram. For this, the support moment diagram will be, so here this is one column, second column, third column. So here at 1 it is minus 245.22, therefore this is minus 245.22. This is minus 45.9, minus 45.9. This is plus 45.9. This is plus 141.66. This is minus 141.66, and here it is 0. Therefore, this will cause tension on the outside. So this will cause tension on the inside. This will cause tension at the bottom. This will cause tension on the top fiber. This will cause tension on the outer side. This is 0 because it is a hinged support, right? D is hinged. Therefore, that is the moments. Now, we have to draw the bending moment diagram. Support moment diagram first. Support moment diagram is we'll mark on the tension side 245.22. So this is 245.22. This is inside 45.9. This is 45.9. This is the bending moment diagram for the column. Now for this beam, again this is 45.9, and here it is 141.6, and here it is 45.9. So this value is 45.9. This is also 45.9. Now this value is 169. This value is 149.66. 141.66. Now here this causes tension on the outer side. Therefore, here it is 145.66. This value is also 145, and here it is 0. This is the support moment diagram. On that, we have to superimpose the simply support moment diagram. The simply support moment diagram for this. So mu AB equal to WL by 4 for a simply support beam subjected to central constant load. So this is WL by 4, that is equal to 48 into L is 12 by 4. So 3 144 km/meter. So here this is 149. Support simply support moment diagram will be 140 there. So this value is 144 km/meter. For the other span MABC, mu BC equal to W L square by 8. For a simply support beam subject to the UDA, it is W L square by 8. W is 24 into L is 6 meters, 6 square by 8. So W L square by 8, this will become 3. So 3 into 3, 36 into 6, 36. 36 into 3, 36 into 3, 108 km/meter, which will be parabolic. You know, you can just draw this diagram neatly. So you have to superimpose the simply support bending moment and support moments and get the bending moment diagram. So this is how you have to get the final bending moment diagram. So the viewers are advised to check up the calculations. Hope it is perfectly alright. You can check and resolve it out to complete the bending moment diagram for a frame, geometrically unsymmetrical as well as loading also unsymmetrical. So we have covered two frames. One is symmetrical, the other one is unsymmetrical. We have covered two problems. One is with the static indeterminacy 3, the second one is with the static indeterminacy 2. So that will give you an idea, because when you choose a problem with the static indeterminacy 3, we have to form the A0 matrix, which will be of size 3 by 3, and invert it. So getting inverse of a 3 by 3 matrix, of course you can do it easily in a calculator, but we can choose for suppose if you are expected to do two problems, one on matrix flexibility and matrix stiffness, it will give you an idea which problem to be chosen. So that will be, I think that will be enough for portal frames. Other problems, the viewers are advised to go through any standard textbook and you can just learn. And I have been asked by one friend through YouTube, so he has represented me to ask me to do one problem on a continuous beam with the settlement of supports. That will take in lecture number 9. So two problems on continuous beam, two problems on portal frames you have completed. Next you have to take up redundant pin jointed frames. Before taking pin jointed frames, I will satisfy the requirement of one viewer, or maybe professor or student, I do not know. But anyway, I will just do one more problem tomorrow. Then from next class onwards, we will take redundant trusses. So that's what about today's lecture on portal frames. Thank you for listening. Thank you.